Hey, this is a video where we're going to start talking about electronegativity differences and polarity of molecules. So, do you remember what electronegativity is? Um, Electronegativity is the tendency of an atom to attract electrons to itself. If you remember, it's kind of like a tug of war, between if elements were people. Who's going to pull on electrons, like if we had two electrons, if this was fluorine and maybe this was, I don't know, oxygen, fluorine's going to be able to pull those electrons closer to itself. The electronegativity values are on our periodic table. This one isn't ours, but you can see sometimes they're a little different. Like ours, I think this is 4.0, but the larger electronegativities are going to be over here with the nonmetals. So bond character, there's the two types of bonds, ionic and covalent, but we can break the covalent bonds into two different types. One of them being nonpolar covalent, which means they're sharing the electrons equally. So in my little cartoon, it's the people sharing the electrons, which would be the blanket, equally. And then there's also a polar covalent where they're still sharing, but just not equally. And then it gets to the point where the difference in electronegativity is so great that there's that transfer of electrons from the metal to the nonmetal. It's really not quite like this. It's not really this definite, but it's kind of a gradual change from being nonpolar to ionic. But this is kind of how we just kind of try to simplify it. And when we do, we use electronegativity differences to classify the type of bond. So if they two elements have a difference in electronegativity of 0, obviously they're nonpolar. They're going to share those electrons perfectly equally. But we also think up to about 0.4. They're not quite equal, but really small difference. That's a nonpolar covalent bond. Polar covalent is when you're getting, greater than 5.5 up to 2.0. And then ionic is when the difference is 2.1 or greater. But there are some times where pretty much if it's a metal and a nonmetal, even if the difference isn't 2.1 or greater, we would call the bond ionic. So here's an example. CCl4 is used as a dry cleaning solvent or cleaner. The structure, you don't need it really, but I'm going to draw it. And what we're looking at here is what kind of bond is there, one of these bonds. And all we do is we look up the electronegativity of the two elements. It doesn't matter that there's 4 chlorines because we're only looking at one bond at a time. And then when we do that, so carbon is 2.5 and chlorine is 3.0. So the difference is 0.5. And remember from that last slide, that then, I'll show you, 0.5 to 2.0 is polar covalent. So this is a polar covalent bond. Sometimes we want to represent, when we do have a polar covalent bond, which element is becoming partially negative, which will always be the one with the higher electronegativity. And then the one with the lower will be, I can't spell this right now. I feel like I have too many letters there. Anyways, these are Greek letter lowercase delta, so it's a partial negative and a partial positive. They're not positive and negative. They're not cations and anions. So that's why we use these symbols. Another thing we can do is an arrow. And the arrow is kind of has a positive part of it, which is going to always point away from the one that has the lower electronegativity. and then it's going to point towards the one that has a higher electronegativity. So I'll show you. So here's an example, hydrogen HF. We first of all should determine the type of bond. So we would look up fluorine's electronegativity on our periodic table, and hydrogen is 2.1. So then the difference is 1.9. So it's a very polar bond. Remember, it's still under 2. Remember our categories? Where are they? So 1.9, we're still in this category, but getting closer to being ionic. So how do we show that? With a dipole arrow, we would point it in the direction of the fluorine and away from the hydrogen, because the fluorine has a higher electronegativity. We can also use the partial charges. So now we're gonna, that was bond polarity. Now we're gonna talk about the molecular polarity. So the whole molecule can be polar, which means it's called it's a dipole. So the whole molecule can be negative on one end and partially positive on the other. And when they are polar molecules, they will align themselves to an electric field. So this is showing the B has a higher electronegativity. Let's say it's 4.0, and maybe this one's only 3.0, we'll say. So we know there's your dipole arrow, and there's our partial charges. It's also going to align itself so the negative end of the molecule is attracted to this positive plate. And then it is possible for a molecule like this one, it's kind of hard to see because they're using gray, but there are polar bonds. So the carbon and oxygen, oxygen is 3.5, carbon is 2.5. So it is a polar bond. But then overall, this is a non-polar molecule. So you'll notice there isn't, I'll show you, we're going to look at this FET a little bit. So when we're running the FET, I think I have it ready. What I wanted to show you is, I'm going to go down, except for that's in the way. We'll go to real molecules. So this is something, if you haven't done the FET that goes with this lesson, you'll want to do it like right when I'm done talking, and not watch the rest of the video till you've done it, because this is a really good way to try to understand it. So here's that hydrogen fluoride that we had in our note example. So the gold arrow is showing that this molecule is polar. So if you have a gold arrow, that means it's pointing towards the end of the whole molecule that is partially negative. So let me just show you a couple other examples. So like carbon dioxide, like that one I was trying to show you, there's no gold arrow. So this is a nonpolar molecule. So essentially those polar bonds kind of cancel out. So that's what you're going to look at, and you're going to notice there's, things that you're going to discover. So like here's a tetrahedron. And, these bonds are polar, but there's no gold arrow. So it's kind of like they're canceling out. You can also show the electrostatic potential, where the color here, there isn't really a huge red or blue because it's a nonpolar molecule. So if it's red, really bright red, it's negative on that end of the molecule. And if it's the dark blue, then it's positive. So this one doesn't really have that. You can also use that one, but I like this one better. So let me show you an example like this one. Turn that off for now. So this one does have a gold arrow. So it is going to be negative on the end that has the fluorine. There are polar bonds for all of these, but this one is not going to cancel out. So then when you click on this, you do get that blue and red. So it's, positive on the end with the hydrogens and negative on the end with the fluorines. So highly recommend that you do the PHET before you do the next part of this lesson. So I'm going to continue. So which shapes are always polar? Bent and trigonal pyramids are. And linear, 2-atom linears if they're not the same element. So bent, I don't bend them when I draw them, but in pyramids, you can see if there's lone pairs on the central atom. So these are lone pair electrons, then it's always going to be polar. And then the linear, if you have two different elements, they'll be polar also. And when we do molecular polarity, we don't really calculate the bond polarity. There's always some, even if it doesn't register over, 0.4, there's still polarity unless they're identical. So these are shapes, linear 2-atom molecules that are not the same element. Trig pyramids and bent are always polar shapes that are always polar. And then the ones that are sometimes polar, and again, I'm going to go back to that PHET because it shows it really well. I'm going to turn that off. So if you have a trig, this is a tetrahedral, if the atoms around it are all the same, like here, they cancel out. And then on paper, this one kind of looks like it would cancel, but you got to remember it's not flat. So if the atoms around, like here you have 2 fluorines and 2 hydrogens, if they're not all the same, then it's going to be polar. If they are all the same, like this one, then it's nonpolar. They cancel out. So tetrahedrons are nonpolar as long as all the atoms going around the central atom are the same. Similarly, we have the trig planar. So remember, this is different than pyramidal. There is not a lone pair on that central atom. So as long as they're the same going around, they cancel and they're nonpolar. But if they're not the same, then they are polar. Similarly, 3-atom linears, as long as these 2 atoms around the central atom are the same, it will cancel and they'll be nonpolar. But I can show you, where are they? They're hiding. This one is linear 3-atom, but the nitrogen and the hydrogen aren't the same, so this is a polar molecule. So these are the rules essentially then. If the atoms around the central atom are the same for trig planar, tetrahedral, and 3-atom linears, then those shapes are nonpolar. If they're not the same, then they're going to be polar. So here they're all the same, nonpolar, nonpolar. Here you have a different one, polar. So if we go back to our notes, our molecular shape notes, we can, this shape is going to be polar. You could write your rule here. So tetrahedrons are polar, or you could write it in, I like to write them as nonpolar if the atoms are the same around the central atom. And then trig pyramid, always polar. Bent, lone pairs on the central atom, always polar. Linear, this one's polar because the elements, 2-atom linear, the elements are different. Then if we go to the next slide, remember this is trig planar, nonpolar if all the atoms around the central atom are the same. This is a bent. Again, there's a lone pair on the central atom, so always polar. And then again, a linear, like this one, if the elements are the same, they'll be nonpolar, but if they're not, then they're polar. So here we have those linears. So this one, again, if the atoms, they're nonpolar, if all the atoms are on the central atom are the same. So then I would recommend that you get your worksheet out here and you can do them and then check with me, but I'm just going to decide whether these are polar or nonpolar. So I'm looking at the shape here, or I can look at the name of the shape. This one's polar. This one is also polar. It looks like they're going to cancel, but they don't, because remember, it's three-dimensional. Next one is polar. If this were a fluorine, it would be nonpolar. Next one's polar because it's a trig pyramid. It has a lone pair on the central atom. Next one would be nonpolar. Next one is a nonpolar. There's no electrons on the central atom. It's linear, and they're the same atom on the sides. Nonpolar, polar. Then we get here. This would be polar. Oops, my pen isn't working. Nonpolar. So even though there's a double bond in there, there's still the same atoms going around the central atom. Next one is polar. They're not all the same. Polar has a lone pair. Nonpolar, they're all the same around the central. Polar, polar, and polar. I hope that helps.